So first, exam 2 is a week from Friday. Let's go up through, so the topics for this. So it starts at the beginning, it's cumulative like always, and let's go up through stresses due to bending moments. So that's what we're doing now. We'll finish that by Friday, so you'll have a lot of time to absorb this stuff. Any questions about the tests? Any homework questions? You just had 1 or 2 problems doing stresses due to tension. Okay, so we're talking about, so back to stresses due to bending moments. And we were working on the area moment of inertia. And remember what the area moment of inertia is. It deals with the geometry of the cross section. And it's a measure of how effectively, how well the cross-section geometry resists bending. Okay, and I gave the example of like a piece of paper. Maybe something rigid is a little easier to picture, but okay, think of the calculator, you know. If you were gonna apply big bending moments about this axis, okay, you can imagine right now that at some point, maybe I can even see it as I do it with my hands. I can cause this to bend about an axis in this direction, okay? But if I did it like this, I can't see it bend no matter how hard I do it. And that is because we saw when I went through the integral for the area moment of inertia, that the area moment of inertia for a rectangular cross section has the height of the cross section cubed and the width just a linear term. And so if for the same amount of material, if you use that material making it taller, you get something that's much more effective at resisting bending. If you use all that material making it wider and you don't make it taller, you have a cross section that's much less effective at resisting bending.
So does that mean that something that's like 3 times as tall is like 27 times?
Yes.
More resistant to bending?
Well, yes, if the width is the same, that's right. And you see that on, so
The beams for the 35W bridge over
yeah, I
the
mean,
river were like 9 feet tall.
yeah. So, right, if you know the direction that something's going to bend, that you're worried about it bending, then you just want to make that as tall as possible to resist that, and you're not too worried about the width. This is just in my head because I was just like looking at some video of it recently, but if you look at the way like musical instrument tops, like stringed instrument tops, the things they do to keep it from collapsing is, so an instrument top, there's really no way around making it very thin and flat because you want it to vibrate. But making it very thin, flat makes it very susceptible to bending, and that bending would be caused by the strings. Can you picture what I'm talking about? I'm talking like a crazy person.
You're talking like the head of a drum.
Okay, so here's like a all 3D version of a guitar, you know.
Guitar.
Thank you. It was $2,700. Okay, so okay, and you have the strings. Let's make this a one-string guitar. Whatever. Okay, so this makes noise because that string makes the top vibrate. Okay, and you need that top to vibrate, so you can't make it too thick. But the problem is that this string is applying a moment to the top that is trying to make this top bend, warp, you know? You can think it's trying to peel this back off like a tin can, you know? And so what they do to keep this relatively thin wooden top from bending so much that it's damaged is underneath that top. So now we're looking at the top from the side. Okay. They put braces on this like this, and then, you know, they'll put them in different directions. I think they usually do it in sort of an X pattern. And, you know, people have put a lot of thought into, and over the centuries or whatever, people have come up with effective ways to brace this. But so the idea is that individual spots on the top can vibrate, but they have these vertical beams basically that have that are oriented in such a way that the bending you're concerned about is restricted. Okay, so that's the idea. So now I'm going to give you just the list. There's only 3 of them. The area moments of inertia of simple shapes. And all of these are about the shape's neutral axis. And remember that how do you identify the neutral axis? It goes through the shape centroid. Okay, so the first one is a rectangle. This is the one we did the integral for. So let's say that we have a height h, and a width B for base. And the neutral axis is, it goes through the centroid, so it's like that. So this is our axis A. And the area moment of inertia about A is 1/12 times the base times the height cubed. So that's the formula we came up with, whatever day it was, Monday. And there you see that relationship that explains why you brace a guitar top this way. The next one is for a circular cross section. We're going to say that this has a radius r, and the neutral axis goes through the centroid. The area moment of inertia for this cross section is pi r to the 4th over 4.
Are these neutral axes parallel with the x-axis?
Yes.
Okay, so this would be bending or area moment of inertia about x?
About z, because this is a cross section.
Oh, okay, I see. So you
Yeah, so
like looking down the x-axis.
yeah, exactly. This is like you're looking at the beam, daring it to stab you in the eye.
Okay, I got it.
So x is coming this way, y is this way, and z is this way.
And then if it's like a tube, you would just take the outside minus the inside.
Yes, but there's some stuff you have to think about. If they have the same center, that's all you have to do. But if they don't have the same center, then we have to talk about what you do then.
That's fair.
No. And then the last one is a rectangle.
Wait, wasn't that the first one?
Yeah, what I mean is a triangle.
That's a funny
I'm still working on my shapes. Okay, so where is the centroid of this triangle located? How high?
1/3.
1/3, yep. So there's the centroid. There is the neutral axis. So this is the, try to draw a little, okay. And the area moment of inertia about that neutral axis is the base times the height cubed over 36. So as long as you calculate the moments of inertias of the simple shapes, like as long as they have the same neutral axis, you can just add and subtract. But if they don't, you have to use a parallel axis theorem. There's a parallel axis theorem just like there was with the mass moment of inertia in dynamics. So parallel axis theorem. So if you have some arbitrary shape, and say that the centroid of this shape is here, and that means the neutral axis is here, and you want to calculate the area moment of inertia about this line, Those two are parallel. That's why it's called the parallel axis theorem. Then the area moment of inertia about A is the one about the neutral axis plus, I mean, based on what you know about the parallel axis theorem in dynamics, based on what you know about the definition of the area moment of inertia, give me your best guess for what the parallel axis theorem part is.
Distance squared.
Distance squared times one thing, because, and in, what?
Mass?
Times the area.
Area, exactly,
Area
right.
moment.
So in mass, moment of inertia, it's mass times distance squared. Here it's just area times distance squared.
Too much in my head with dynamics and Deform
Yeah.
at the same time.
But, so if you play this right, you can store both of these two in one spot in your brain, you know,
I mean, is that
and
like-
leave the rest for Futurama.
I mean, it's pretty easy to see where I went wrong. It's called the area moment.
Yeah, exactly.
But it's so is the like moment of whatever, does that always have to do with like a distribution of something from
It always has to do with a distance, and the first moment is just the thing times the distance, and the second moment is the thing times the distance squared. And so these are both second moments
of some
Yeah.
property?
of some property, correct?
And it's just the area of the whole body, right?
Yes,
The
that's
area
right.
of the-
Yep. And
cross-section.
Or the cross section.
yeah, so let me put that in here. So this is the area of the cross section. And this one you get from the formula, you know. One thing to notice about this is the smallest, so given a certain shape, the smallest the area moment of inertia can be is about the neutral axis. Because you're adding on something positive times something squared. So you can't do anything but get bigger as you move away from the neutral axis. Okay, so when would you have to do this? Because we calculated the, I gave you formulas for the area moment of inertia of these shapes about their neutral axis. So, and the formula that we're using for stresses deals with the moment of inertia about the neutral axis. Okay, so why would you ever need to do it somewhere else? Well, it's if you're adding or subtracting shapes. Okay, so let's do an example like that where we have a complicated shape made up of simple shapes. Okay. And so let's say our beam is like a T shape. The beam is like this. Our coordinate system is the same as it always is, with x going this way, y this way, z this way. And the dimensions of the cross section are 0.5 meters. That's a big beam. 0.5 meters like that. The thickness is, all the thicknesses are the same, 1 centimeter. and the distance from here to here is 0.5. Okay, so I'm going to break this up into a rectangle here and a rectangle here.
What's the width of the middle?
That's also 1 centimeter. So the first thing we have to do, so basically we're going from so we have to calculate the area moment of inertia of this about its neutral axis using the formula, that's easy. The area moment of inertia of this about its neutral axis, that's easy, okay? But then we have to figure out where the neutral axis of the whole thing is and use the parallel axis theorem for each of these to move the axis away from its own neutral axis. Then we can just add them. Are you with me on that? I mean, it's the same approach that we use in dynamics. So the people taking dynamics right now, you're getting sort of used to this idea. All right, well, in order to find the neutral axis, so first find the neutral axis of the whole thing. And that's just a matter of finding the centroid. Where do I want to put that? I think I'll just put it down at the bottom. We don't have to calculate, the x doesn't matter at all. We just have to calculate that height. So if this is shape 1 and this is shape 2, let's start with 1. The area of shape 1 is 0.5 times 0.01, so 0.05 meters squared. And the centroid of 1, I'll write it like this, is, well, we know that it's 0.005 above the bottom. And we know that to get to the bottom from our coordinate system, you have to go up 0.5. So this is 0.505. I put my coordinate system somewhere else before, so those stupid notes don't help. Okay, with me on that?
I think it's supposed to be 0.005 meters.
It's 0.005. So where I have the coordinate system, it's 0.005 from here to here.
No, I mean the area.
0.0.
I think you're just missing 0.
Okay, thank you, great. You're right.
Mm-hmm.
Okay.
Shouldn't it be 0.495? Because that's above the shape.
The 0.5 goes from to the bottom of the top. Yeah, that's not super clear. Let me change this a little. Okay, so now we're going to do shape 2. And that one's easy. It's just 0.25. The area is, these are the same. the centroid is positive 0.25. And now we can calculate the centroid from the bottom. So the total area is 0.01 meters squared. So the total centroid is 1 over 0.01 times the quantity 0.005 times 0.505 plus 0.005 times 0.25 0.3775 meters. And that's from the bottom. Okay, so now we're going to calculate the area moments of inertia of each of these two shapes, but we have to calculate it about this location. Okay, so now we'll go back to rectangle 1. And the moment of inertia is 1 over 12 times the 1/12 base times. Okay, so 1/12 times, so for this first one, the base is 0.5. And the height is 0.01. And then we're going to do the parallel axis theorem part. Okay, so this is going to be the area, 0.005, times the distance from the centroid of 1 to the centroid of the whole shape. So you can think of, so the centroid of 1 is 0.505, the centroid of the whole shape is 0.3775, so you can just subtract those. So this is 0.1275, square that. And I get 8.54, let's keep a few digits, 48 times 10 to the minus 5.
What are the units?
The units are meters to the fourth. One thing to notice here is that this parallel axis theorem part, the contribution from the shape itself is tiny compared to the contribution from moving the neutral axis. Okay, and that's something you're taking advantage of when you make I-beams or whatever. You're taking, so like in an I-beam, the horizontal parts of an I-beam, if you just made the shape, the whole cross section of the beam, the horizontal part, it would bend really easily. Okay, but you take those same shapes and move them away from the neutral axis, you get this big contribution so that those two short, stubby, things actually provide a lot of resistance to bending because you've moved them away from their neutral axis.
Does that have to do with like buckling or something?
It just has to do with it just has to do with the bending formula. And I wrote that in the notes last time. We haven't used it yet, but the stress due to bending is just the bending moment times the height above the neutral axis divided by this I. And so if you can make this I big, you make the stress small. Okay, so now the second shape, I2 is equal to 1/12. This time the base is the little one. So this one, the shape itself works pretty well at resisting bending. So we have 0.01 times 0.5 to the third. And now plus the parallel axis theorem part, so that's 0.005 times the distance here is 0.3775 minus 0.25. So that's 0.1275 squared. And I get 1.8545 times 10 to the minus fourth. Now that we have both of these calculated about the same neutral axis of the whole shape, now I total is just the sum of these two. Okay. Damn it. Ah, I erased it. Okay. Wait, 0.5448 times 10 to the minus 5 plus 1.8545 times 10 to the minus 4. And we get 2.709 times 10 to the minus 4 meters to the fourth. Any questions about that? Okay, so now we're going to put this into the stress equation. So let's say we have this cantilever beam. And we're ignoring the weight. This has a length of 1 meter. And let's say there's a 1,500 Newton force this way and an external couple of 200 Newton meters that way. And the cross section of this beam so let's do it 2 times. We'll first do it with a square. Where each of these is a centimeter. No, 10 centimeters. What's the, so 0.01. Okay. And then second, we'll do it with the cross section from last time. And notice that these two cross sections use the same amount of material. So these beams are the same amount of material. Okay. So the beams for parts A and B are the same amount of material. And let's say that we want to calculate the stress in the center of the beam. It actually doesn't vary by X in this case, but at the top of the cross section. Okay, are you picturing everything going on here? So what would you guess is going to happen here? How are these stresses going to relate to each other? I mean, given that, so the basic idea is this is a fairly effective way to use material to produce a big moment of inertia. So what do you think is going to happen if we have a big moment of inertia versus a relatively small one? What's going to happen to those stresses? So the stress, our goal in designing something like this is to reduce the stress. So this square cross section is going to have a bigger stress at its top than the one with the better engineered beam cross section. Okay, so we're looking for part B to just have lower stresses. That's our goal. Okay, so first we have to solve the internal loads. Oh, one other thing. So that's a weird way to produce a bending moment. Why did I do it with that couple at the end? Why didn't I just put a downward force at the end here?
To keep it one cut.
If I put a downward force here, it would still be one cut. But the problem is, if I did that, we'd have non-zero shear forces the whole way. And we don't know how to calculate stresses due to shear force yet. So this way, all we're going to have is internal tension, compression, and internal bending moment. And so we can calculate the full stress tensor. Okay? Are you with me on that? Tension. I'm going to change one thing actually here. Let's make this go the other way. So the way this is now, this 1500 newtons is going to put the top of the beam in compression. The whole thing is going to be in compression. Now doing this, the bending moment is also going to put the top in compression. So those two aren't going to, so we're not going to see those two counteract each other. They can do that. But in this case, each one is going to make that stress bigger. Okay. All right, so we have a reaction force, I'll just call that R, and we have a reaction couple, I'll call that MR, and then we have 1500 here, and 200 Newton meters here. Newton's second law says R minus 1500 is equal to 0. So R is equal to 1500 newtons. And the moment equation about the z-axis, we have MR plus 200 is equal to 0. So MR is equal to negative 200 Newton meters. Okay, and now we'll do our one cut. These are for x values between 0 and 1. So we have a force of 1500 here, a couple of 200 like this, and then we have our internal tension and our internal bending moment. Newton's second law says 1500 plus T is equal to 0. So T is negative 1500. That says that this is in compression everywhere. Does that make sense? Is that what we expect? Yeah, I mean, this force is just trying to smush this thing against the wall, so it's in compression. And then the moment equation about the z-axis, we have negative 200 plus m is equal to 0. So m is equal to positive 200 Newton meters. Okay, so now we have these two internal loads. And now we can, these are the same no matter what cross sections we chose, but now we can do the different cross sections. So let's do cross section A first. So for the tension compression, we know that sigma xx is equal to the internal tension divided by the cross-sectional area. And we can trust these signs always. So this is negative 1500 divided by a cross-sectional area of 0.01. And so that is negative 0.15 times 10 to the 6, right? That's right. And so the stress tensor due to tension compression is negative 0.1500, zeros everywhere. This is megapascals. So that's what we did before. And now we're getting to the bending moment. So we're talking about that square cross-section now. So the area moment of inertia about the neutral axis is 1/12 times the base times the height cubed. And so that is 8.3 repeating times 10 to the minus 6th meters to the fourth. And now the formula for the stress due to the bending moment is negative m times y over I. We can trust the signs on this. Our m is positive, so we have negative 200 times y. This y is for, where did I say this? We're calculating this at the top of the beam. So y is the height difference from the centroid of that square to the top, which is 0.05. And then divided by the area moment of inertia of that whole cross section. That doesn't change point by point. And so we get 1.2 times 10 to the 6 pascals.
Negative.
Yes. As a stress tensor, so the stress tensor due to the bending moment is negative 1.2, zeros everywhere else. And this is megapascals. All the other internal loads were 0, so all we have is these two. And so for this square cross section, the total stress tensor is the sum of the one due to internal tension plus the one due to the bending moment, and that is negative 1.35, zeros everywhere else. Okay? Any questions about that? So, yeah.
So when you said calculate the stress at the center and the top, did you mean
The stress.
like, or
Oh, at the center, I mean.
is that from like the center to the top?
No, I mean, by the center, I meant along this cross section.
Oh, okay.
But it was the same at everywhere along the beam anyways. So this is the X location.
But if we did it in like the center of the cross section, the Y part of the MYI would have been 0.
0, that's exactly right. Yep. So if Y is equal to 0, you're along the neutral axis. And remember, the definition of the neutral axis is that there's no change in length.
So
remember that?
There's no stretching or compressing
Right.
material.
And because we have linear stress strain, if there's no strain, there's no stress.
Okay.
Yep. So along the neutral axis, there's no stress due to bending. There's stress due to other stuff, but not bending. Any other questions? Okay, so we'll So this is what we're comparing to, and we expect the stress in a more effective cross section to be smaller than this when we do that T cross section. Okay, that's all.